Hello, everyone, and welcome to today's webinar. My name is Celeste Schroep, and I will be your moderator for today. The topic for today's webinar focuses on extractive metallurgy of zirconium and hafnium, looking at both current practices and future directions. Our speaker today is Dr. Michael Moats from Missouri S&T. Before we get started, I want to go over a few logistics for our webinar today. Next slide, please. So this is a webinar presented by CMI and hosted by Colorado School of Mines. We welcome any suggestions for future webinars and other topics. You will receive a survey following today's webinar where you can present those future ideas, or you're welcome to email us at cmi@mines.edu. This webinar will be recorded and will be posted on our YouTube channel, Critical Materials Innovation Hub, in about a week's time. You can also find it at aimslab.gov/CMI, my apologies. Throughout the webinar, please feel free to ask questions in the Q&A box. Pop them in at any time when you have them in your head, and we will address those at the end of our presentation. So to kick us off, I'm going to introduce our speaker really briefly, and then I'll hand it off to him. So Dr. Mike Moats is a fellow of the Society of Mining, Metallurgy, and Exploration. His work spans process development, electrochemical and solution-based separations, integrated flowsheet design, and critical minerals processing. He serves as the area lead for the Enhancing and Diversifying Supply within the Critical Materials Innovation Hub. He has lots of experience and lots of knowledge to share with us, so I'm excited to hand it off to Mike for his presentation.
Oh, thank you, Celeste. Appreciate it. And thank you all for joining us for the webinar. I'm going to talk to you about zirconium and hafnium. I had the opportunity to visit the Western Zirconium plant when I was a professor at the University of Utah many years ago, and I thought the chemistry and metallurgy was really fascinating. And so when CMI asked if I would be willing to give a webinar, I thought this would be an interesting topic. I didn't appreciate maybe how interesting it would be, so I've got a lot of ground to cover. I will try my best to tell you all about how zirconium and hafnium is produced. It's been in my mind recently about zirconium and hafnium because of all of the information that's coming out with data centers and the small modular nuclear reactors that companies are talking about installing. And these are the needs for the energy to supply the data centers, which has to do with all of the AI revolution. And so there's lots of news articles here. You can go find them all over the place where there's these thoughts of bringing small modular reactors all over the place. In fact, my university is thinking about bringing a small modular reactor. We have a small 50 kilowatt reactor here at Missouri University of Science and Technology, and we're looking at bringing in a small modular reactor and creating what we call the Powerplex. So interested about this technology, and in fact, the World Nuclear Association just published a report earlier this year saying that it's the government targets and the potentials and everything that's been proposed over the next 25 years, you're going to see a tripling of the nuclear fleet. So from maybe 400 gigawatt capacity up to 1,400. And so anytime you see a tripling of something over the course of about 25 years, the question, of course, then comes, do we have the capacity to do that? And in their outlook, I just grab a quick snip of their outlook, and we'll just say that there's a significant increase to support the tripling of the global nuclear power. And of course, the reliable availability of materials is really important. Specifically, they call out zirconium. And so that's why it's kind of been at the thought of my process as, area lead, thinking about enhancing and diversifying supply for energy here in the United States. And if we're going to be building all these nuclear reactors, do we have the zirconium that we need? Now, zirconium is really the cladding on the fuel rods. So there's some sort of nuclear fuel, it goes into a rod. We need a material that doesn't absorb a lot of neutrons and is also structurally sound, very strong, but also corrosion resistant, because of course this sits inside of a water, usually a water system. And so when you look at all of those things, doesn't absorb neutrons, is structurally sound, and is corrosion resistant, zirconium quickly comes to the top of the material selection, and so that's why we have zirconium cladding. When I'm preparing the slides, I thought, here's something I didn't know. There is a unit called the barn. Apparently, it's a thermal neutron cross section, and so it is equivalent to 10 to the minus 20 square meters of cross-section, neutron cross-section. And so the lower the number, the less neutrons are absorbed during fission generation. And when the early part of the nuclear energy development, they were looking at materials like magnesium and zirconium and aluminum because they were pretty low. But zirconium had a lot of different variation, and as you'll see, and that has to do with the hafnium. All natural resources of zirconium contain about 2% hafnium, so that's in zircon. And that hafnium, which you can see has about 104 barns, created quite a bit of variation in the zirconium that was produced, which led to the need to separate zirconium and hafnium. So how did that come about? This was, if you're going to get into this area with zirconium and hafnium, there's a lot of work that was done by the U.S. Bureau of Mines and other national labs. So an MIT professor, Dr. Kaufman, basically looked at the variation of differences in absorptions cross sections published in zirconium in the early 40s or mid 40s. And he realized that, and working with some Oak Ridge scientists, Oak Ridge National Laboratory, they realized that variation had to do with different concentrations of hafnium in the zirconium. So that led to the need to separate the hafnium from zirconium, which led to processes that were developed by Fisher and coworkers at Oak Ridge, and they started really investigating the process and scaling it up. At the same time, Admiral Rickoff in the Navy said that the zirconium canning was going to be used for the nuclear submarine program, so there's a great need for the nation. And just think about this in today's world. So they started developing the process in 1947. They started piloting it. They turned it over to the U.S. Bureau of Mines, who went to Albany, Oregon, started construction of an industrial-sized plant in 1951. They completed construction in 1952, and were making low hafnium zirconium to help with the nuclear submarine programs by April 1952. So pretty much in 3 to 4 or 5 years, they went from lab concept through piloting, through construction. And this image right here is a picture from the archives from this paper internal report of Bureau of Mines back in 1959 when the facility was being built in Albany, Oregon. Hafnium is also needed for nuclear energy, but also aerospace. So the hafnium that we separate isn't just thrown away, it's also very valuable. Hafnium, because it has that higher neutron cross-section, is used as control rod. So you can see the control rod sticking up out of the reactor here. And all the control rod does is they can lower or raise this to allow for more neutrons to flow between the control rod or between the fuel rods, which provides more energy to heat up the water. You lower them and you slow down the reaction. So this is a way to control the reaction and be able to control your reactor. Most of the hafnium in the world actually is used in aerospace applications, but again, we're focusing on nuclear energy in this talk. Hafnium and zirconium are really important for the application. Okay, so let's get into the extractive metallurgy. We need zirconium and hafnium. Most of the world comes from a silicate mineral called zircon. About 1.2 million metric tons of zircon is mined per year. The leading producers are Australia, South Africa, Mozambique, China, and Senegal. The United States produces less than 100,000 metric tons of zircon a year. The exact amount is withheld by USGS to maintain confidentiality. But most of the world is produced, most of the zircon is produced in Australia, and they also own most of the reserves. And you can see that it's bounced around over the years, but basically zircon comes out of Australia, and it comes from mineral sand deposits. And so mineral sand deposits are essentially beach sands, so they can be along an existing ocean, or they were part of a shoreline at some point. They contain lots of heavy minerals, so we basically go through and we separate the mineral and make a concentrate using gravity separation, which are the spirals right here, actually the spirals right here. And then we use magnetic separation to remove things that are magnetic, such as ilmenite and monazite. And then we use electrostatic separation or high tension separation to recover zircon and rutile. So let's talk about those a little bit more details. Basically, spirals are a very easy technology. Essentially, it simulates a river bend. And so as the slurry goes around the spiral, the lights tend to come to the outside, the heavies come to the inside. You can then open up ports towards the inside by moving these levers. And then basically the heavy minerals get collected on the inside and the lights come on the outside. And we end up with different feeds, a light material and a heavy material. A lot of times the lights are rejected and sent back into the pit where they were dug up from the sand, and the heavies move on to other processing. We then go to this magnetic separation where we remove the magnetic materials. So we can either use a low intensity magnetic separation to remove easy magnetized materials like magnetite. Then we can use a high intensity to collect high intensity magnetic separation to collect paramagnetic. So this would be like ilmenite. We can do this dry or we can do this wet. So if you're seeing this and you're going into this research, if you see a W in front of it, that just means it's wet. So this would be a wet high intensity magnetic separation. On the back end, occasionally we use induced roll magnetic separators where the electromagnetic field is separated. Basically, we tune using electricity the specific magnetic field. There's a lot of different types of magnetic separators. There's countercurrent, concurrent, and counter rotation. They each have their own utilization. Wills is a very common mineral processing handbook. So if you'd like to learn more about mineral processing and magnetic separation, that would be a good place to start. Coming out, we've got the gravity concentrators. We get heavy, the higher density materials. We do magnetic separations. And in the non-magnetic, it ends up your zircon and rutile, same thing. You do typically dry them. We don't usually do high tension separations wet. And high temperature tension or electrostatic separation, essentially, we have a coroned electrode which charges all the particles. There's a conductive drum, and the particles that are conductive lose their charge, and they fall off the drum as it's spinning. The non-conductive do not lose their charge and eventually come around and either form non-concentrates or some midland streams which are reprocessed. You usually put rolls in verticality. So here you can see some rolls that are high tension rolls that are here. And so basically if you look, here's conductive, here's conductive, here's conductive. And so we end up with a concentrate that had to be 3 times a conductive material. And this is how we make a separation. And then, of course, the plant metallurgist decides what they're going to do with the midlands. So you can see the non-conducting material is where the zircon. So in this case, it would be sticking to the drum, sticking to the drum, sticking to the drum, and they end up with zircon here. And this is how we make concentrates. And so when you think about zircon production, of course, it also is then tied to ilmenite production, rutile production, and maybe even monazite production. Most of the zircon in the world does not go to metal production. Zircon is used heavily in making tiles and ceramics. Zirconia or zirconium chemicals. So of course we had to take a picture of the cubic zirconia. So if that's what's on your finger, congratulations. Also refractories. Refractories inside of furnaces heavily use zircon, excuse me, and also in metal foundry and casting. You'll notice if you add these up, it's 100%, and metals aren't listed anywhere. That's because in the zircon industry, metal is considered a zircon chemical. And so actually the metals are inside of this 20%. Now this next slide I'm going to tell you, I'm not going to really talk through it. I just want to give you an idea of this is how complex the zircon industry is. So the zircon stand can go to any number of different applications. The one we're going to talk is way over here to the right, going to zirconium metal. Okay, so this is what we're going to focus on over here. But to say, if you're making extractive metallurgy, you have to understand that most of the world's zircon does not go into the metal. So when you're looking at zircon to zirconium, the established methods, there's multiple routes. Excuse me as I'm getting dry mouth. In the United States, we do carbochlorination, which I'm just going to say is CC around here. So we take the zircon and we go through carbochlorination. We then go through a solvent extraction process using methyl isobutyl ketone, or IMBK. The French do something different. They go through carbochlorination, but they go through a distillation process, and we'll talk a little bit about this. Obviously, I'm in the United States, and we're going to talk a lot about the United States process. India has a separate process. Japan has a separate process. Russia has a separate process. There is no one process to produce zirconium metal. And I think that's the most important thing for me to give to you is there's a lot of exciting chemistry, a lot of really interesting chemistry for zirconium. And there's lots of ways to proverbially skin the cat to do this in different ways. And so it leads for a lot of opportunities. Now, that also means there's a lot of open literature on this. And it'll take you quite a bit of time to go through all of that to make sure if you're thinking of doing something new in this area, that it hasn't been done already. But I'm going to mainly focus on the American process and talk a little bit about the French process, because I don't have enough time in 30 minutes to do otherwise. The two American plants are in Albany, Oregon. The Albany, Oregon plant is operated by ATI. Historically, that plant was operated by a company called Huacheng. Huacheng did buy the original U.S. Bureau of Mines plant. It became too small, and so they built a bigger plant. So while the original U.S. Bureau of Mines plant was in Albany, this is not the same plant. Similar technology, just not the same plant. Historically, some people left Huacheng, went to Utah and created their own plant, and that's Western Zirconium. And so Ogden, Utah, just north of the Salt Lake City, near the Salt Lake, is owned by Westinghouse. And a lot of times you'll just see this plant referred to as Western Zirconium. Both use the solvent extraction for hafnium zirconium separation using the MIBK process. When you look at it, just some cartoons. We're going to take zircon, we're going to mix it with carbon and some chlorine gas. This is the chlorination furnace. Zirconium hafnium chloride comes out. There's some purification in the sublimation furnace, which may happen here, or it actually may happen before the Kroll reactor, depending on the plant. We go through a separation. This can be solvent extraction. This can be distillation. We end up with zirconium tetrachloride and hafnium tetrachloride. We then go to zirconium tetrachloride ends up in a Kroll reactor, which we end up with sponge of zirconium. The hafnium can also be gone through a Kroll reactor and vacuum induction, but hafnium can also be produced electrochemically. We'll talk about that at the end. The main thing when we look at zircon is you have obviously silicon impurity that you have to remove. We have to get rid of the silicon as part of the silicate. And then we need to get, if we're going to make nuclear grade zirconium, then we need to get rid of this hafnium, which is about a 50-to-1 ratio. If you're not making reactor grade zirconium, then the hafnium doesn't have to be removed. It doesn't hurt your metallurgical properties. It doesn't hurt the corrosion aspects of it. So the only time hafnium needs to be removed is for nuclear grade materials. The other thing I think that's important to realize is that the zircon industry has limits on norm. Norm means naturally occurring radioactive materials. And so there's two specifications that's quoted in the literature, that uranium plus thorium, it has to be less than 500 ppm, or that uranium plus 0.4 times the thorium concentration has to be less than 100 parts per million. And that's, of course, that means if you're going to start dealing with zircon to create zirconium or zirconia, you have to be careful about the resource, the material that you're getting. Naturally occurring zircon may be slightly radioactive, and you have to be careful of that. More details about the flow sheet that we're going to talk about. This is what's being done in Oregon and Utah, is that basically zircon is mixed with petroleum coke, is put into a fluidized bed reactors where chlorine gas is the reactant and the fluidizer. Hafnium zirconium chloride comes off as a gas, goes through condensers, and basically comes out as a solid. It's kind of an interesting chemistry that there is not a stable liquid phase, so immediately goes from gas to solid. Silicon tetrachloride also forms as a gas from the zircon, excuse me. That condensing point is much lower, and so it actually condenses out as a liquid eventually. And then we're going to take that zircon and zirconium tetrachloride, hafnium tetrachloride, and we're going to go through solvent extraction. We're going to separate them. The hafnium is going to come out, and we're going to go through a calcining furnace to make a hafnium oxide. The zirconium tetrachloride comes out. We precipitate it, go through through a calcinizing kiln to make zirconia, excuse me. We are going to go through a carbochlorination furnace to put it back to zirconium tetrachloride, and we're going to go into the Kroll process, where zirconium is reduced by magnesium and then distilled, and we eventually get this zirconium sponge. And I'm not going to go any farther than that in the discussion. I'm just going to stop at zirconium sponge, because the rest is, we'll say, more physical metallurgy than extractive metallurgy. So in carbochlorination, zircon flour is mixed with coke. It's introduced into a fluidized bed. Chlorine gas is the reactant, and the fluidizing gas, there's the reaction. The zirconium tetrachloride and the silicon tetrachloride are both gases. So the chlorination temperature is between 1,000 and 1,200 degrees Celsius. They then go through condensers where the gas is cooled off. Zirconium tetrachloride, hafnium tetrachloride forms a solid around 330 C, so it'll form a solid and we'll capture those. The gas will continue to be cooled. Silicon tetrachloride forms a liquid around 58 degrees C. That is sold as a product and is used in various chemical processing. It's a high pure form of silica tetrachloride. You have to worry about impurities. Some impurities stay as a residue that's in the carbochlorine. They don't form volatile chlorides, so they stay in the residue in the carbochlorination reactor, but some do, and you have to treat them later on. To purify those silicon, purify the zirconium tetrachloride and the hafnium tetrachloride, there's various patents that are out there, but basically you sublime them, you heat them up to gases below hydrogen and nitrogen, and that allows for some of these impurities to be removed. And I'll show you how to do that. But there's other techniques to how to do that. Iron can also be removed during the solvent extraction phase. So if you're going to be studying or looking at removing other impurities during this process, then you're going to be looking at sublimation or maybe solvent extraction. So we've got to zirconium hafnium separation. So we have a zirconium hafnium chloride. It's a solid coming out of the condensers. That's dissolved in an aqueous media. That aqueous media depends on the type of solvent extraction that is used or the type of separation. Historically, fractional crystallization, so preferential precipitation can be done. It's very intensive from a number of stages. People have been looking at ion exchange more recently, but most of the plants in the world use solvent extraction. In solvent extraction, the United States uses the chloride system. So we dissolve the zirconium tetrachloride, hafnium tetrachloride into a chloride-based system. And then we complex it with thiocyanate and then do solvent extraction with MIBK. In India, they dissolve it in a nitrate system and use TBP. In Japan, they use a sulfate system and they use an amine to do the solvent extraction. So again, lots of fun chemistry, lots of different ways to do this. So what's practiced in the United States, and it's probably a busy slide. If Scott McCall's on the line, he's probably making fun of me right now. And so basically what we have is the chloride is placed in a 1 molar HCl, 1 molar thiocyanate solution. The thiocyanate forms a complex. So we have a zirconyl thiocyanate and a hafnilyl thiocyanate. The hafnilyl thiocyanate is extracted by the MIBK, which is saturated in thiocyanate. So we basically have some sort of stage, solvent extraction stage, where the feed material comes into contact with the organic. We have thiocyanate coming around. And so basically we have the organic loads the hafnium, gets a little bit of zirconium on there, so it has to be stripped off. We use HCl to strip the zirconia. And so basically we have the strip or scrubbing that comes off and comes back around. The zirconium that doesn't load is the raffinate. We recover the thiocyanate by adding HCl here. So the thiocyanate is regenerated and sent back around. And then the zirconium, which is now a zirconium chloride, it then comes around and is precipitated with a sulfuric acid matrix, then repulped with an ammonia solution to finally lead to a zirconium oxide after calcination. This zirconium is less than 100 parts per million hafnium, which is considered hafnium-free by the nuclear industry. The organic, which has hafnium in it, has to be recovered. So hafnium comes along, and it's stripped using sulfuric acid. The organic is then regenerated. And so the MIBK that's saturated with thiocyanate comes back around. So there's extraction, there's stripping, there's scrubbing, there's solvent regeneration, and thiocyanate recovery. So it's a fairly complex system, but we end up with this hafnium typically has about 0.5 to 1% zirconium. You can get it lower, but you have to do more purification. So some pictures from an old plant. So this was, again, another report from the U.S. Bureau of Mines. And so here are the pulse solvent extraction columns. So these are packed bed pulse columns that are used in Albany. So if you're not familiar with the pulse column, basically the aqueous comes in from the top, the organic comes in the middle, the organic goes up, the aqueous comes down, and every time you have a different plate, or this is considered a stage, so you can get lots of stages in one column, and you can see that they have lots of different columns. So there are a lot of different stages to get this hafnium zirconium separation. There are problems with the MIBK system, not ideal. First of all, it's soluble in water, so as you're doing this process, you're losing the MIBK, and so you're having to replace it. And then this was, again, a U.S. Bureau of Mine report that was looking at a different system, and he was looking at zirconyl sulfate, and I just pinched this directly from it, quoted it, so you can see all of the issues. There's air pollutants, there's a notoriously catty smell, which I wonder what exactly that means. You also have leakages, and you have the fact that you're dealing with a volatile material which can pose fire hazards. Obviously, the people in Albany, Oregon, or Ogden, Utah, are operating under their regulations. I don't doubt that they are not doing that. But MIBK could be something that we could look at and investigating replacing. I'll be honest, the Chinese have done quite a bit of work in this area. There's an interesting paper published in an obscure Arabian chemical engineering journal where they basically call out a replacement for MIBK. So again, a lot of literature that you're going to have to explore if you're going to look into this. I'm going to move on. I could talk about other solvent extraction systems, but I was afraid I was going to be running out of time. So I want to go to extractive distillation. So the French nuclear industry was working closely with the United States industry in the 1960s and 70s. And in fact, the first hafnium zirconium separation plants in southern France were very much similar to the U.S. Bureau of Mines process or the Oak Ridge process. And along the ways, they decided they wanted to do something different. And so there are differences in the vapor pressure of zirconium tetrachloride and hafnium tetrachloride. Now, if you just do it by itself, this is what the plot looks like. And at any given temperature, the vapor pressure of the hafnium tetrachloride is a little bit higher. So you could maybe volatilize the hafnium away from the zirconium. And there are systems based purely on this, that you just heat this up and you can get distillation differences based on vapor pressure. It takes a lot of stages. And so it's not been commercially utilized. But what is utilized in the extractive distillation, and therefore pyrometallurgical, the system, is doing this, but doing it through a molten salt. So the key patent was Besson in 1977 et al. And basically what happens is the crude feed, the zirconium tetrachloride, hafnium tetrachloride that comes out of carbochlorination, is fed into a column where a tower where molten salt, and here it says aluminum trichloride, but really it's an aluminum chloride, potassium chloride of a very specific ratio. And the aluminum tetrachloride is trichloride, is actually lost in the process a little bit. So you have to add it to keep this ratio the same. And basically what happens is in this molten salt, the hafnium volatilizes and the zirconium gets absorbed into the salt. And so zirconium comes out the bottom and hafnium comes out, and then we go through the cooling stage like we always do to get this hafnium tetrachloride salt back. The zirconium that comes out, they actually blow then nitrogen gas through the molten salt because zirconium tetrachloride has vapor pressure, just not as high as the hafnium tetrachloride. And so again, it comes up and we condense it. And so by extractive distillation, we don't have to go through solvent extraction, followed by precipitation, followed by recarbochlorination. You get rid of all those steps in between. When this came out, there's a lot of the U.S. Bureau of Mines reports basically saying, yeah, this process is better than what we have. The problem with this is you have all this nice gas running around at high temperatures. So materials of construction are a problem. You have to use very expensive materials of construction, and controls are also really, really important. But this is the plant in France and how they do that. If you want to look at distillation processes, I know you can't read this slide, or I can't read this slide without my glasses on. The point here again is there's a lot of different systems that have been looked at. And if you're going to go down this road, understand that you should look at what's been done in the 1950s, 60s, and 70s, because there was a lot of work done. Okay, we now have, if you're coming in the United States, you have materials coming out that have gone through calcining kilns and they're oxides. We go through a chlorination again, just like I talked about before. I'm not going to rehash that. Or if you're coming out of the France plant, you immediately come into this with zirconium tetrachloride, hafnium tetrachloride somewhere else, and we're going to go into the Kroll process. Now, what you can see in this flow sheet, which I pinched from earlier in the presentation, this is where we do sublimation. This is where we heat the crude zirconium tetrachloride, which may still have some impurities in it. And basically what we do is we heat this up, and because of vapor pressure differences, we then condense a refined zirconium tetrachloride. The impurities are left behind. That material is then transferred to a reduction furnace, which is a Kroll furnace. And in this, I'll go through more. This is where we do the magnesium reduction. Then we create zinc sponge, and we go to a distillation furnace, which then gives us to a zirconium sponge. I probably said zinc there. So the Kroll process was developed in the 1940s, really for titanium. Titanium and zirconium are usually reported in the literature together if you're reading reviews. So the technology is very similar. And so what happens in the Kroll process is it's a two-part container that's put inside of a furnace. It's called a pit furnace because it's usually dug into the ground. Zirconium tetrachloride is loaded into the top, and there is a channel or a tube that comes between the bottom half and the top half. The two halves are welded together, and we put magnesium ingots in the bottom. We heat this up, and that gives us reduction. That creates a zirconium sponge, but it also creates magnesium and magnesium chloride, and we need to separate those. So that material is transferred over to a distillation process where this is heated up. The magnesium melts, the magnesium chloride falls down, and we're left over with a zirconium sponge. So I'm going to go through reduction and distillation. So in reduction, basically once you fill this up and you weld it, you have to remove all the air. You then backfill with argon to make sure there's nothing here, because if you heat this up in the presence of oxygen, you can have real problems. There's also water vapor that's absorbed by the zirconium tetrachloride solid, so you need to heat that up to remove the water. So as you're heating this up, you're venting until you reach a critical temperature and when you no longer see the pressure building up. You then heat the upper zone. It's separately heated, and you sublime the zirconium tetrachloride. It makes the gas and comes down this center pipe. It then reacts with the magnesium that's melted, and that creates a vapor pressure. And so you basically start to get a reaction, and you get magnesium chloride and zirconium particles. Magnesium actually floats on top of the magnesium chloride, and the zirconium particles settle down to the bottom. It's a very exothermic reaction, so temperature runaways have to be very closely monitored, and therefore they're pulling energy out to keep it at a very fixed temperature, which leads to long reaction times. So people have looked at how to replace this because this may be a many hour operation. We'll just say it that way. Upon cooling, they take out the zirconium sponge. You have to be very careful because now you've made a porous zirconium. It reacts with air, and so they bring it over to a furnace. They heat this back up. The magnesium and magnesium chloride end up in the bottom. You end up with these sponges of zirconium particles. They do sinter together, but voids remain. And so when you pull it out of this furnace, you have to be careful. In fact, this reference basically talks about zirconium catching on fire and how to put it out. That's what you end up with is a zirconium sponge. That sponge is crushed up into chunks and then goes on for nuclear. I'm not going to get into how to make tubes and whatever. I focused all this time now on zirconium. So what about the hafnium? Okay. So that hafnium that comes out of either extractive distillation or by solvent extraction and then secondary carbochlorination, I end up with a hafnium tetrachloride. We can go through the Kroll process and make hafnium sponge like I just said. You can also go through molten salt electrolysis, and this is actually practiced in France. So I'm going to talk a little bit about molten salt electrolysis. If this purity, this 0.5 to 1% zirconium is not is not good enough purity for what you're trying, you can refine it. It's an older process called the iodide process, or you can do what's called e-beam melting, and that's needed when you need a good cold roll ductility for the hafnium. In hafnium electrolysis, essentially the hafnium chloride goes into a molten salt of equimolar sodium chloride and potassium chloride. There's a little bit of sodium fluoride that's added, and that's to basically stabilize the hafnium ions in the molten salt, increase current efficiency, and prevent sublimation of the hafnium chloride. And basically, we go through a molten salt electrolysis where the hafnium crystals are grown on typically a graphite or inert electrode, and we have a graphite electrode on the other side. These are just plots to show that the hafnium is produced, can be deposited at a much more positive potential than the other elements that will be in this molten salt. So there's a pretty big window for them to deposit out and be a fairly pure hafnium material. So I have blown through extractive metallurgy of zirconium and hafnium. Okay, and as I look at this, when I think, oh, where could I make a difference? I think the first thing is I underestimated when I agreed to do this talk how much background material and how many different things, and I didn't even cover all the different processes. So I'm just going to warn you, the audience, if you're interested in this area, the literature is extensive, so you need to do your homework. I'd say in mineral processing, the fact that there's a norm standard that's naturally occurring radioactive material, so is there a way to do better separation there? Is there something there you can do? Conversion of zirconium tetrachloride and zirconium oxide, there's some kinetic works that's been done recently in this area, but it seems to be pretty well, the technology seems to be pretty mature. On zirconium hafnium separation, I've taken some ideas and liberties from these recent articles. I think, you know, there's always need for better fundamental chemistry understanding, especially these systems are very complex. You know, as I sit with my CMI hat on, and I think of some of the things that we're doing in the CMI, I think could there be a better or different extractant that's generated from computational chemistry, re-looking at some of the systems. Is there a complexing agent that's different than thiocyanate? Thiocyanate is has some issues to it, especially if there's an accidental release. Can we develop some more selective ion exchange resins and get away from solvent extraction altogether? On the reduction to metal, you know, I've always, whenever I teach on the Kroll process, I'm reminded that Kroll thought his process would only last for about 10 years before it was replaced by something else. And here we are, darn near 80 years later. So a lot of people have tried, but that means there's a lot of literature for you not to try. And so people have tried electrolysis for zirconium like they have for hafnium. And so maybe there's some different things that we've learned for rare earths and for other things right now that we're looking in molten salts that can be applied to zirconium. Because really the zirconium process for magnesium reduction really came from titanium. There is quite a bit of work on zirconium oxychloride or carbide, excuse me. So this would be heating up with a carbothermic reaction and then maybe treating that electrochemically. So there's some different pathways. And of course, there's pathways that I didn't have time to cover today. So with that, I hope that was informative, and I'm happy to try to answer any questions.
Awesome job, Mike. I really appreciate all the visuals that you provided. As someone who doesn't have a background in chemistry, it was very helpful to kind of see those processes laid out like that. So it looks like we do have a couple questions in the Q&A. If you want to take the first one and read that out for the collective, that would be wonderful.
So can molten salt electrolysis done on hafnium be also done on zirconium? So people have tried that. I don't remember all of the details. But people have tried that. So is it viable? You know, economic viability is very challenging, Joshua, because if the plant is already built, then you have a barrier to changing your process because I've already built the process. So the question is, if you're going to do a greenfield, if we're going to really triple the production of zirconium and hafnium, what would you do from scratch? And that's the time to put in the new technology. The problem is you have to have the technology so well documented that engineering companies are willing to put it in and provide performance guarantees. So zirconium can be electro one from molten salt. And I'm going to point you at the literature as to what things are maybe that, could be improved. How do you deal with safety and environmental contamination with those volatile chlorides and chlorine gas? And so, Paul, I guess I don't work at the facility, so I don't know exactly how to answer that, other than they've been operating now for darn near 70 years. And so they obviously are doing that. And so I don't have an answer other than make sure that your pipes don't leak. And I know that's probably flippant, but I think that's really is that. Oh, Martha, it's good to see you. Thank you. Extraction efficiencies and costs. I won't comment on costs because costs are really hard to get. The Indian process, dissolution in nitrate followed by TBP, the literature seems to indicate that it takes more processing steps and it is not as efficient chemically as the MIBK thiocyanate process. And then France is extractive distillation, so it's very efficient. The Japanese use the sulfate and amine process, and I'm going to guess they think it's more efficient because those plants were built later after the U.S. plants were done. So I guess I will. There's more to it. Is the flow sheet described by the type of feed or availability of inputs? Almost everything comes from zircon. There is a little bit of natural occurrence zirconium dioxide. As far as I can tell, that's pretty much in Russia, and it is processed in Russia. I will say that the South Africans, I didn't mention them, have their own process where they do some plasma treatment of the zircon as well. They make a glassy silica and then a zirconium dioxide, which then you can go to carbochlorination through. So I don't know. There's so many options there. I don't think I'm just going to give a high level answer of it depends. Okay. Hello. 2 questions. This is from John. It is my connection that the text is not readable at present and will be uploaded version with higher resolution. Okay. Will this cover crystal bar production? No. Any other questions?
Looks like there's one more.
Okay.
Or a couple more. Maybe I just have to refresh.
Oh, okay. I'm sorry. I was starting at the bottom. I'm working my way up. Okay. Starting. Are you aware of or versus the tantalum chloride extraction process? John, I'm not familiar with that, so I can't comment on that. Hi, Steve. How are you? Have you seen hydrogen reduction of these metals? Steve, I didn't come across that research. I was mainly focused on the industrial processes that we're using. I know that they use hydrogen for sublimation to remove impurities, but I didn't actually focus on reduction to metal, so I can't comment on that. So there's a question about reduction with fluorides with calcium instead as done with REEs, and could you compare that to or as an alternative for Kroll process? And I'll say that I've seen the literature where people have looked at moving away from the chlorides and going to the fluorides, either for differences in vapor pressure or because you could do the calcium reduction as in with the rare earths. So I know that is a current direction of research, but I don't know that I have an opinion on it.
Awesome job. Thank you, Mike. Great job going through those questions too.
Sure.
If anybody has any last minute thoughts for Mike to pop that into the Q&A. If not, I'll start wrapping us up with our last slide and reminders. As a reminder, this webinar is recorded and will be available on our YouTube channel in about a week's time and also on our website at aimslab.gov/CMI. We will have details for our next webinar in the future and in our Critical Times newsletter, my apologies. So keep your eye out for that and also post it on our social medias. If you have suggestions for future webinars, please feel free to share those with us by either emailing us at cmi@mines.edu or completing that post-webinar survey that you'll be receiving in your inbox shortly after the end of our webinar today. But with that, I think we are good to call it end of our first Microsoft Teams webinar. So thank you so much, Mike, for your participation today, and those of you joining us, and we hope to see you next time.